This is a video on the central limit theorem. What we'll be talking about is first something called sampling distributions, which has to do with taking a look at all possible samples of a fixed size and looking at the data you get from those samples. Then we'll look at the big theorem of the entire term for this class, and that's called the central limit theorem. And then we'll look at two variations on that. The first will be the central limit theorem for sums, and the second is the central limit theorem for proportions. First, let's define sampling distributions. So here's how it works. For a sampling distribution, what we say is that given a population and sample size n, the sampling distribution of a statistic is the distribution of all values of the statistic for all possible samples of size n. So let's suppose you wanted to find out, I don't know, what the average weight is of Americans. You can't get them all, so we know that we can maybe survey 50 of them. Well, we could also think about what would it be like to survey every possible group of 50 Americans about how much they weigh, and maybe take the average of them, or the standard deviation, or the range, or any of the different statistics we've had. Each of those averages we can list, and we look at the distribution of that list. And that's going to be what the sampling distribution is all about. I'll give you some specific examples soon. But first, let's talk about the biggie, and that is a sampling distribution of the mean. And it's the same idea, except now we're specifically talking about the mean. Given a population and sample size n, the sampling distribution of the mean is the distribution of all the means for all possible samples of size n. And in particular, we have some special notation for this. So if you look at all the possible means that are sample means from samples of size n, and we look at the mean of those sample means, then we call that mean mu sub x bar. Because we're looking at all the different sample means, and we're looking at all of them, we think of it as a mean if you're taking the average of them all. But it's a mean of a bunch of sample means, so that's the mu for the population mean of the sample means, x bars. The standard deviation of all those possible sample means is noted as sigma sub x bar, because it's a population standard deviation for all possible sample means. Population standard deviation is sigma, sample mean is x bar. So let's take a look at an example. So suppose we have a family. We got a little infant. He's 2 feet tall. Then we got a cute little toddler. She's 3 feet tall. We got maybe an elementary school, maybe a first grader. He's 4 foot tall. And then we got our middle school girl, and she's 5 feet tall. And what we want to look at is we want to look at samples of size 2. So let's look at the different samples of size 2 from this family. Well, we could take the infant and the toddler. And if we do that, we have a 2 foot tall kid and a 3 foot tall kid. The average of that is x bar because it's a sample. And the mean of 2 and 3 is 2.5. We could then take the infant and this first grader. And that is 2 and 4. The sample mean is 2 plus 4 over 2, which is 3. We could take the infant and the middle school kid. That's 2 and 5, and its sample mean is 3.5. We can keep going. We could take the toddler and the first grader, and we get a sample mean of 3.5. We could take the toddler and the middle school kid, and we get a sample mean of 4. And then finally we could take this first grader and the middle school kid, and that has a sample mean of 4.5. So notice we now have a list of 6 different numbers. That's different than the list of 4 numbers that we started with. Notice that the sampling distribution is a distribution of a different group of numbers than the population distribution. The population distribution's mean, for example, is 2 plus 3 plus 4 plus 5 divided by 4, which happens to be mu equals 3.5, mu for the population mean. I put these numbers 2, 3, 4, 5 in my calculator, and I got a standard deviation of 1.12 for the population standard deviation. Now let's take a look at the sampling distribution. I could look at the mean of all the sample means. So that's 2.5 plus 3 plus 3.5 plus 3.5 plus 4 plus 4.5 divided by 6. And when I do that, I got 3.5. I got the same number. It turns out that is not a coincidence. It turns out the sampling distribution for the sample mean will have a mean, a population mean of the sample means, always equal to the population mean that we started with. On the other hand, if I take the standard deviation of these 6 numbers, what I get is sigma sub x bar is 0.79. It's smaller than the population standard deviation that I started with. That's a good thing. You always want smaller standard deviations if you can get them, because then you get better estimates. Less risk in finance, which we'll see in a little bit. This sigma sub x bar comes up so often that it has a special name. We call that the standard error. So the standard error, sometimes we say the standard error for the mean, is 0.79. So let's do a simulation. So this is a little simulation that I built. And what I'm going to do is I'm going to start out with a normal distribution of population mean 200 and population standard deviation 67, about. And I want to find out what the sampling distribution looks like. Let's choose n equals 100 to start with. So if I choose n equals 100, then the sampling distribution, notice, is also approximately normal. The mean is approximately the same, and it'll be exactly the same if you look at all possible ones. This computer just selected several thousand of them, much more than I'm going to do by hand, but a computer doesn't get bored. But the standard deviation for the x-bar distribution, or the standard error, notice is much smaller than the original standard deviation. It's 6.7 about. Notice that's about 1/10 of the original 67 we started with. Okay, that's pretty important because we had n equals 100 and we reduced by a factor of 10. 10 just happens to be the square root of 100. That's not a coincidence. That always is true, as we'll see in the big theorem, which we will call the Central Limit Theorem. Let's try another example. This time let's pick a uniform distribution just for fun. Same mean and about the same standard deviation. 115 will be our standard deviation. U is 200. And let's try n equals 36. See what happens. So we saw that if we started with a normal distribution, we got a normal distribution when we looked at the sampling distribution. Now if we start out with a uniform distribution, what distribution do you guess we might get for the sampling distribution? Well, let's try it. Ta-da! We didn't get a uniform distribution either. This doesn't look uniform at all. But what it does kind of look like is approximately normal, right? Notice it's symmetric, it's approximately bell-shaped, just normal, and normal is good. Our calculator even has a normal distribution function. Notice the mean stayed about the same, but the standard deviation didn't. it got reduced. We started with about 115, and we ended up with about 19. And notice that 115 divided by the square root of 36, 115 divided by 6 is around 19.32. Not that far off. So that's going to be our big theorem of the day. This even works with some fun distributions. So if I start out with, let's do an interesting distribution. Let's make it, I don't know, let's put a little skyscraper in here. Maybe a condominium. How about a little mound? And just all kind of funky stuff. Okay, so here's the distribution. So if we do a sample of size 2, do you think we'll get a normal distribution? Let's take a look. Not quite. Okay, it's all over the place. It's not what we started with. It's not normal. Samples of size 2 don't turn out to be very good. On the other hand, if I do a sample of size 100, then it looks more approximately normal, somewhat bell-shaped. That's always going to be true, that we get a normal distribution as long as either we start out with a normal distribution or we have a large sample size. Then we'll get something approximately normal. And that's going to be the big thing for our central limit theorem. So let's go back to our PowerPoint and look at the central limit theorem. And what it says is, let's suppose that x bar is the mean for a random sample of size n from a population having mean mu and standard deviation sigma. Then mu sub x bar, the mean of the sampling distribution, is always exactly equal to the mean of the population distribution. And sigma sub x bar, the standard error, or the standard deviation of the sampling distribution, is always exactly equal to sigma divided by the square root of the sample size, no matter what the distribution was that we started with. But if the distribution that we started with is normal, then the distribution of x bar, the sampling distribution, is also normal for any sample size n. And if the distribution may not be normal, no matter what the distribution is, as long as we have a large sample size, then the distribution of x bar, the sampling distribution, is approximately normal, regardless of what the original distribution was. And a rule of thumb for our class is going to be that n greater than 30 is going to be considered to be large. Some people consider 25. I like 30, it's a little safer. If you really want to be safe, then give large sample sizes, bigger than 100. But for our class, we're going to just let 30 be good enough for our approximation. This is the most important theorem of the entire class. It allows us to do a lot of things. It means that if we're taking samples, then we know that the sampling distribution is normal as long as our sample size is large enough. And that's important because we can compute probabilities when we have normal distributions. But we don't know how to compute probabilities if we don't know what the distribution is for the original samples. That's huge. But remember, if you have a normal distribution and you want to compute a probability, you must know what the mean is, and you must know what the standard deviation is. So, in particular, we do know because we have the central limit theorem. It also tells us that sigma sub x bar is sigma divided by the square root of n. So if we want a very small sampling distribution's standard deviation, or a very small standard error, then all we have to do is use a very large sample size. And then we know that we're going to be very close. Our x bar is going to be very likely to be very close to the original population mean. So that means surveys with large sample sizes very likely will have a sample mean that's close to the population mean. That's really, really important. So let me talk about one more thing before I go on and use it and find these probabilities. So we saw with our little cute family of 4 kids that our population mean was 3.5. Our mu sub x bar, of course, was also 3.5. That's a good thing. That means, or what we're going to say, is that when we have this case, then x bar will be called an unbiased estimator. So that means that mu sub x bar was the same as mu. So the question is, if you have a sampling distribution like so, then is any statistic an unbiased estimator of its corresponding parameter? So x bar is an unbiased estimator of mu because mu sub x bar is equal to mu. In other words, is the average of all the means equal to the population mean? Well, let's take another example. Let's look at ranges instead of means. Is the average of all the possible ranges of these samples the same as the population range? Well, the population range is really easy to figure out. That's just the high number minus the low number. 5 minus 2 is 3. So the population range is 3. So the question is the average of all the ranges of these 6 samples also equal to 3? Let's look at the ranges of the 6 samples. The first is 3 minus 2, which is 1. The second is 4 minus 2, which is 2. The third is 5 minus 2, which is 3. The fourth is 4 minus 3, which is 1. Then 5 minus 3 is 2. And 5 minus 4 is 1. Let's look at that. I think it's really clear to me that if I take the average of 1, 2, 3, 1, 2, and 1, I'm not going to get 3. I'm going to get something lower than 3. And in fact, if I work this out, I actually get the average of all these ranges is 1 2/3, or about 1.67. So we missed. Mu sub range is not equal to the population range. So mu sub sample range is not equal to range. So what we say is that the sample range is a biased estimator for the population range. This is really important because what this tells us is if we collect a sample and we find the range for that sample, that's a really bad guess for the range for the population. On the other hand, if we find the mean of a sample, that's a very good guess for the mean for the population. So let's look at some other statistics. So first, we say an estimate is unbiased if the following happens. A statistic whose sampling distribution has a mean that is equal to the population parameter. And if that statistic has that mean that's equal to the population parameter, we call it an unbiased estimator. We saw that the sample mean is an unbiased estimator for the population mean. The sample proportion also turns out to be an unbiased estimator for the population proportion, which means that if you do a survey and it's a yes or no question, then the proportion for that survey is going to be our best guess for the population proportion. Similarly, the sample variance is an unbiased estimator for the population variance. But the sample range, we saw, was a biased estimator for the population range. One thing I left out here, kind of on purpose, is the sample standard deviation. It turns out that the sample standard deviation is slightly biased. It is biased, but only by a little bit. Okay, so now that we have all of our framework for understanding sampling distributions, let's look at some examples. So the first example I have is the following. Suppose the average amount of time that it takes for college students to complete their degree is 4.7 years. And let's suppose the standard deviation is 0.3 years. The question is, what is the probability that 40 randomly selected college students will have an average completion time of less than 4.4 years? Notice that we don't know what the distribution is for completion times for students. It could be skewed left or right or normal. We have no idea. But because we are doing a sample of size 40, we can look at the sampling distribution and invoke the central limit theorem, which says that if we have a large sample, and we do, 40 is large, larger than 30, then we can say the sampling distribution is also approximately normal. And that means we can compute probabilities using the normal distribution, which we can do with our calculator. Isn't that wonderful? So now let's look at our numbers. We had our mean was 4.7 for the population. Sigma was 0.3, n is 40. We want the probability that x bar is less than 4.4. And the central limit theorem tells us that x bar is approximately normally distributed, with mean 4.7 because mu sub x bar is the same as mu. On the other hand, sigma sub x bar is not the same as sigma. It's not 0.3. It's 0.3 divided by the square root of the sample size. So 0.3 divided by the square root of 40. So because it's normally distributed, we could draw this beautiful picture of a normal curve whose mean is 4.7 and find out the area to the left of 4.4. And we know how to do that using our calculator. So now let's go to our calculator. So here's our calculator. We have a normal distribution. So I can go to second distribution, and I can go to normal CDF and hit enter. We wanted to find out the probability that x bar is less than 4.4. So that means the left-hand side is negative infinity. Remember, we use negative 999 will be good enough, comma, 4.4, so the low then the high, 4.4, then comma, the mean was 4.7, 4.7, comma, and the standard deviation was 0.3 over the square root of 40. I could put that directly into my calculator. 0.3 divided by second square root of 40. And I hit enter. Notice we get 1.2754 e negative 10. That does not mean the probability is about 1.3. Don't even go there. Probabilities are never bigger than 1. So if you thought that, that means you didn't look at the e negative 10. That means move the decimal over 10 places. So we get 0.9999999991274, which is basically no probability. It would be almost impossible to sample 40 students and find out that their average time to completion and graduation is less than 4.4 years. So now let's go to another example. Okay, the next example says the following. Suppose the average GPA of college students is 3.1, and the standard deviation is 0.7. A class of 35 randomly selected students will be considered high risk if their mean GPA is in the bottom second percentile. What is the largest mean GPA that will be considered high risk? So first, notice that our class is 35. That is bigger than 30. So the central limit theorem guarantees that the sampling distribution will be approximately normal. Notice that saying that we know the sampling distribution is normal is different than assuming the sampling distribution is normal. So Get that difference. Assume is a bad thing. That means there's a good chance or a chance that it's just wrong. When we know that it's normal, that means it's right. So we can conclude the distribution is approximately normal. So in particular, we can say that x bar is, by fact, approximately normal. The mean will be 3.1 because that was the mean of the population. And the standard deviation will be 0.7 divided by the square root of 35. That's sigma over the square root of the sample size. This time we want to find the second percentile. So that means we want to find out what value of x bar will be such that the probability that that value of x bar being less than this value is less than 0.02 or 2%. So on a graph, we know the mean is 3.1. We don't know the value, but we do know the area to the left of the curve. And we want to find out the value of x bar such that area to the left of that x bar is equal to 0.02. And we know how to do that using our calculators. When we're given a probability and we want to find out the value on the horizontal axis, that's when we go to the inv norm. Let's go to our calculator. Okay, so here's our calculator. I go to second distribution, and I hit 3 for inv norm. And then here we type in the 0.02 first, 0.02 for the second percentile, comma, and then if you remember, our mean was 3.1, comma, and then 0.7 divided by the square root of 35. I hit enter, and there it is. So that means that the second percentile for the classes of size 35 will have a GPA of about 2.86. So let's look at another example that I find quite useful because it has to do with investing. Okay, so here's the next example. Suppose stock increases are normally distributed with a mean of 3% and a standard deviation of 5%. So if it's a good year, you could think of this as quarterly. If it's not such a great year, you could think of this as annually. If your randomly selected portfolio consists of 20 stocks, what is the probability that your portfolio will lose money? So we want to look at this as, is it better to have your money in 20 different stocks? Or maybe it's better to just throw all of your money in one stock and see what happens. And what I want to look at is risk factor. You want to find out what's that probability you're going to lose money? What is your risk of ending up with losing what they call the principal, the money that you put in? So again, here we have a sample size of 20. When we have that, we cannot conclude without any other information that our sampling distribution is normal. We must assume, there's this suppose, that the distribution of the stock market is normal. I have no idea if that's true, but if it's true, then we can do it. If it's not, then we really can't do this. We better have more than 20 stocks if we want to do the calculation. We better have more than 30, in fact. So in particular, our mean was 3. I'm going to call it 3 instead of 0.03. That will work as long as you use percents as units instead of decimals. So 3 for mu. Sigma was 5%, so 5. N was 20. And x bar is less than 0. We want to find out the probability that x bar is less than 0 because you lose money. if you end up with a negative return. So we can use our central limit theorem. X bar is approximately normal because our original distribution was assumed to be normal. Our mu was 3. And our sigma sub x bar is 5 over the square root of 20. We could draw a picture of this. Here's good old 0. The mean was 3. We want to find out the area to the left of 0. So now we go ahead and use our calculator. Let's do that. Okay, so here's our calculator. I got a second distribution. Here we want to find the area of the curve given a value of x. So that's normal CDF, which is number 2. We want to find out the probability that x bar is less than 0. So the low will be negative 999, which is approximately negative infinity. The high, if you remember, is 0. The mean was 3. And the standard deviation was 5 divided by the square root of 20. So 5 divided by second square root of 20. And I hit enter. Notice it is 0.0036. That's less than 1% chance of losing money because we diversified our portfolio with 20 stocks. Again, we're making some assumptions. Randomness is a big assumption. They're independent, normal distribution, all kinds of assumptions. But it really does work that if you have a diversified portfolio, your risks is much smaller. So you have less than 1% chance of losing money. What would happen if you threw all of your money into a single stock? Well, that'd be the same thing, except in our calculation, let's go back. I'm going to go second entry, and I'm going to tweak it a bit. That would be the same thing, except that you're not dividing by the square root of 20 anymore. Now, we have a sample size of 1. We're back to the old just normal distribution. I'll type 0, 1. Call that square root of 1. See what the probability is. Now we have a 27% chance instead of around 1/3% chance. So notice that it really changes things to have a large sample size instead of just picking 1. So now let's go back and talk about a couple more details of the central limit theorem. Okay, what we have already done is we've looked at the probability that x bar will be less than a number, or greater than a number, between numbers, however that might be. Sometimes instead of an average, you're more interested in the total instead of the average. So it turns out that if the collection of all random samples of size n are taken from a population having mean mu and standard deviation sigma. So we're looking at the sampling distribution. But now we want to look at the sampling distribution of sums. So what is the sampling distribution of the total? Well, it turns out that their mean will have mean n times mu and standard deviation root n times sigma. That makes sense if you think about it. So for example, if you played a game, maybe baseball, and you found out that the population mean number of runs in baseball was 5, and you looked at a sample of, say, 20 games, then you would expect that the total amount of runs will be 20 times 5, or 100 total runs for those 20 games. You wouldn't divide, you multiply. Similarly, the standard deviation is root n times sigma, and that has to do with if you take sigma divided by root n and multiply it by n, you get root n times sigma. That comes from algebra. I'll let you think about that for a while. And then the normality condition is exactly the same. If the population is normally distributed, or if the sample size is large, then the distribution of the sums is also approximately normal. So let's look at an example. Okay, let's suppose we have a carnival at which the average family at the carnival spends $65, and the standard deviation is $15. If 80 randomly selected families are chosen, what is the probability that they will spend a total of more than $5,000? So we could think of being a vendor and looking at the carnival and saying, well, if we have 80 families at our carnival, are we going to make at least $5,000 at this carnival out of those 80 families? So we don't care as much about the averages that we do the bottom line, which is the total amount of money that these families will spend. So we can use the central limit theorem for sums. Notice also we have 80 randomly selected families, so we don't have to assume we have a normal distribution. We can conclude that the distribution of sums is normal because our sample size is 80, which is greater than 30. So in particular, we could say that sigma x, the sum of all of the x's, is approximately normally distributed with mean 65 times 80, which happens to be 5,200, and standard deviation 15 times the square root of 80, which happens to be about 134. When you put it in your calculator, it's better to put directly 15 times root 80 than to use this approximation. We can draw a picture. We have a normal distribution, so we can draw a normal curve. Here's 5,200. That's the mean. And we want to find out the probability the sum is greater than 5,000. So the area to the right of 5,000. So let's go ahead and do that using our calculator. Okay, so here's our calculator. I could go to second distribution. We want to find the area under a normal curve. So that's number 2. We take the normal CDF. We wanted to find out the probability that the sum was greater than 5,000. So the low will be 5,000, 5,000, comma. The high will be infinity. Now don't use 999 because we already have big numbers like 5,000. So we need to have a whole lot of 9s, like 9, 9, 9, 9, 9, 9, 9, 9. That'll work. That's much bigger than all the rest. And then comma, and then 5,200, 5,200, and then comma, and then it was 15 times the square root, so second square root of 80. And I hit enter. So we could say that there's about a 93% chance that the total amount of money that these 80 randomly selected families will spend at the carnival will be at least $5,000. Okay, now let's talk about, instead of sums, let's see what happens when we have the yes or no question. This is what I call the central limit theorem for proportions. So first, having a sample size greater than 30 is not enough. Okay, we don't need a sample size greater than 30. What we really need is we need to make sure that we expect at least 5 people, actually greater than 5 people, to say yes, and greater than 5 people to say no to the question. Symbolically, we could say NP is greater than 5, and NQ is also greater than 5, where Q is 1 minus P. Then if we have this, then the binomial distribution is approximately normal, with mean mu sub p hat equals p, and standard error sigma sub p hat equals the square root of p times q divided by n. So let me show you how to use this. So here's an example. 12% of the United States population is left-handed. I'm left-handed, so a lot of other people are too. We rule. If 200 randomly selected Americans are surveyed, what is the probability that fewer than 20 of them are left-handed? Okay, notice that 20 over 200 is 10%. So the question is, what is the probability that less than 10% of 200 randomly selected Americans will be left-handed? Okay, notice that if we take NP, that's 20, and that's bigger than 5. And NQ, that's 180. 200 minus 20 are the number of righties, or ambidextrous, which would be also bigger than 5. So I can use the central limit theorem for proportions and say that the binomial distribution is approximately normal, so that the distribution of p hats is approximately normal, with mean 0.12, because that's 12% are lefty, and standard deviation, the square root of 0.12 times 1 minus 0.12, which is 0.88, divided by 200. And we want to find out what is the probability that this sample proportion will be less than 0.1. Well, we could draw a picture. Here's the 12% of the lefties, 0.12. Here's the 10% that we want to find out if we have fewer than 10%. And what is that probability, or what is the area under this approximately normal curve? And I can go to my calculator to find out. Okay, so here's my calculator. I go to second distribution, and then number 2 is normal CDF. Here we wanted to find out the probability that p hat is less than 0.1. So the left is negative infinity, or negative 999 is good enough, comma, 0.1, comma, 12% or 0.12, comma, and now it's the square root, so second root, and then 0.12 times 0.88 divided by 200. And I hit enter. And I get about 19% chance. So there's about 19% chance that if I choose 200 Americans at random, that fewer than 10% will be left-handed. Okay? There's a little bit that I'm not going to talk about called the continuity correction. So if you need to do that, it turns out you're better off using, instead of 10%, 9.5%. I'm not going to go into that detail. But if you're coming from another class, just let you know, if you hear continuity correction, you're going to have to use, instead of 10%, you're going to have to use 9.5%. But I'm just not going to go there, or 9.5. So let's do another example. Okay, so here's the final example I have for you today. According to a recent Gallup poll, 18% of Americans are underemployed. If 150 Americans are randomly selected, find the probability that between 24 and 30 of them are underemployed. Okay, so a couple things. First, notice 18% of 150 is bigger than 5. It's bigger than 18. And the other side of the coin, so that's 82% of 150, is also bigger than 5. So we can use the central limit theorem for proportions. So that's really important. Second, 24 out of 150 turns out to be 15%, and 30 out of 150 turns out to be 20%. So because of that, we want the probability that p hat is between 0.15 and 0.2. We can use the central limit theorem and say that the p hat distribution is approximately normal with mean 0.18, that's p, and standard deviation, the square root of 0.18 times 0.82 divided by 150. And I could find this using my calculator, but first let's look at a picture. We want to find out the area between the numbers 0.15 and 0.2. And again, there is something called continuity correction, which I'm not doing, so if you must do that in your class, then you're going to have to do some more details, which I'm not discussing. Let's go to the calculator and find this probability. Okay, so I go to second distribution, and then I go to normal CDF, hit enter. Our low was 0.15. Our high is 0.20 or 0.2. Our mean was 0.18, and our standard deviation was the square root, so second square root of PQ over N, so that's 0.18, times 0.82 divided by 200. And I hit enter. And there we have it. We can say that if we randomly selected 150 Americans, then there would be about a 63% chance that between 24 and 30 of these Americans would be underemployed. So that's about all I have to say about the central limit theorem. This is a very deep concept, so you're going to need lots and lots of practice working out problems, reading over the PowerPoint again, watching the video, getting help from your instructor to really get the idea of what a sampling distribution really means. The difference between having to assume you have a normal distribution and getting to conclude there is a normal distribution. Understanding and being able to identify totals versus means versus proportions, knowing when to use which, and really getting the central limit theorem and when to use it and how to use it and what it's for. So when you have questions, please either ask me, or if you're in another class, ask your instructor, or ask your friends or a tutor or just anybody to get some help to make sure you get this. The entire rest of the course in elementary statistics really relies on the central limit theorem. It is the theorem for all of statistics that you must really understand. So I hope you can get this and have a wonderful rest of the day or evening or morning or whatever you're at. And thank you again for watching this video.